everybody. This is Nighttime Mathematics Radio. Coming to you live every evening and Saturday at 10 p.m. with the best mathematics tutoring we can and the worst loop sample GarageBand has to offer. If you need math help, anybody, just browse on over to @NightMathRadio on Twitter. Give us a holler. We'll try to help you out. So if you need mathematics help, go over to Twitter, tweet math questions to us at @NightMathRadio. We'll try to get to you right here on the air. Good evening, everybody. It's after 10 o'clock on Saturday evening, so it's time for Nighttime Mathematics Radio. If you have any questions, just tweet straight to us over here on Twitter. We'll try to answer them right live on the air. While we're waiting for someone to tweet in live, someone earlier in the evening had an interesting math question for us, so let's take a look at that. Now, earlier in the evening, somebody tweeted the following question to us, and I'll write it here on my notepad. Somebody said, well, what do we do if I have this question? I've got 2 cosine cubed x. Let me scroll this down so we can see it. Minus 3 root 3 cosine squared x plus 3 cosine x is equal to 0. Now you look at this is a bit of a mess because this has got some trig, it's got a polynomial hidden in there. And the key thing we want to do is address them separately. You don't want to deal with trig and algebra at the same time. So let's define a new variable for a moment. Let's define let u equals cosine x. Because if we do that, that gets rid of the trig for the minute. That gives us just 2u cubed minus 3 root 3 u squared plus 3u is equal to 0. Now that's a lot more plausible looking. We're not talking trigonometry anymore. Now we're just talking algebra. So what can we do with this? Well, we can factor it. We can factor out a u to begin with. 2u squared minus 3 root 3 u plus 3 is equal to 0. Now remember, if this is two things multiplied together equal to 0, that means either one factor has to be equal to 0 or the other factor has to be equal to 0. So either u equals 0 or 2u squared minus 3 root 3u plus 3 is equal to 0. Now, the left one's obvious, u equals 0, but let's look at this right one. That's a quadratic equation. We've got a formula for that. So u is equal to 3 root 3 minus b plus or minus the square root of b squared. Well, 3 root 3 squared is easy. That's 9 times 3 or 27. Minus 4ac. Well, 4 times 2 is 8. 8 times 3 is 24. So minus 4ac is minus 24 over 2a, or 4. Or in other words, u is equal to 3 root 3 plus or minus, check it out, root 3 over 4. So u is equal to 4 at 3 over 4, just root 3, or u is equal to root 3 over 2. Now, if this was actually just an algebra problem, we'd be done now. We know what u can be. But now we have to go back to the trigonometry, because remember, u is supposed to be cosine x. So this says either cosine x equals 0, or cosine x is equal to the square root of 3, or cosine x is equal to the square root of 3 over 2. Now, when is cosine x 0? Well, you can take an inverse cosine. The inverse cosine of 0, remember, is 90 degrees, or pi over 2. But then remember, that happens every pi, because remember, an inverse cosine just gives you the answer between 0 and pi. It gives you that one bit where cosine can pretend to be a function. And then we have to use our knowledge of what trig functions look like to get all the other answers. So when else is it 0? Well, you know it'll be 0 again on the way back up again. So it'll be 0 again at 3 pi. It'll be 0 again at 5 pi. It'll be 0 again at minus pi, oddly enough. And in fact, it'll generally be x will be equal to 2n pi plus pi. Where are we getting this? Let's draw this correctly. Let's make sure we understand this right. The inverse cosine was 0 right at pi here. I'm being stupid. I'm sorry, pi over 2. I'm being dumb. Let's do this right. Inverse cosine 0 is pi over 2. That's the only thing between 0 and pi where it becomes 0. So here's pi, here it's negative 1. Where else can it be 0? Well, it'll be 0 again on the way back up again at 3 pi over 2. And it'll be 0 again on the way back down again at 5 pi over 2. In fact, it'll be there at every integer pi plus pi over 2. And that's the correct answer here. So x is equal to n pi plus pi over 2 for all n an integer. How about the second answer? Cosine x equals root 3. Well, that one we can just cross out. Because why? Root 3 is bigger than 1. And cosine x is only going to be between 1 and minus 1, so that can't happen. The answer's not worth anything. That's useless. And finally, we have cosine x is equal to root 3 over 2. Where does that happen? Well, remember, that happens at pi over 6. How do you know this? Remember, this is one of the things you just memorized. This is how you remember where these things are. So at 0 we have 1, and it goes down to minus 1, and here at pi over 6, it goes through root 3 over 2. But now we need all the other periodicities. So on the way back up to 2 pi, it'll hit it again at 2 pi, up here again, at sort of the reflected point. Where's that going to be? Well, it'll be at 2 pi minus pi over 6. Where's that? Well, that's 11 pi over 6. There's pi over 6. So where are the solutions here? The solutions are at pi over 6, 11 pi over 6, 13 pi over 6. And generally, it'll be within pi over 6 in each direction of every 2 pi. So here, this one will be x is equal to 2n pi plus or minus pi over 6. And that's the solution for this problem. Hopefully that makes sense. Does everyone understand how this works? Remember, these things are tricky. It's easy to get one solution using the inverse cosine. Pi over 2 for where cosine x is equal to 0. Pi over 6 for where cosine x is equal to root 3 over 2. But then you have to remember where all the other ones live. And to get those, you have to remember what the whole function looks like. Cosine is periodic over 2 pi, so it'll be certainly every 2 pi worth of these things. But then also you have to remember the other branch, because cosine over between 0 and 2... Let me pull a new page to show what this looks like. Between 0 and 2 pi, cosine starts at 1, goes at pi becomes minus 1, goes all the way down, then by 2 pi goes all the way back up again. Now what the inverse cosine will give you is the answer between 0 and pi. Pi over 2 in the case of cosine x equals 0, pi over 6 in the case of cosine x equals root 3 over 2, and so on. But it won't give you this other piece. There'll be another one even within the periodicity. Where does that come from? Well, remember, this thing is symmetric around pi. So if there's an answer at pi over 6, there has to be another answer at 2 pi minus pi over 6. If there's an answer at pi over 2, there has to be another answer at 2 pi minus pi over 2, or 3 pi over 2. And then it'll be that plus any number of 2 pi's you add, because the whole thing's 2 pi periodic. This is Nighttime Mathematics Radio. Let's go back to Twitter and see if we've got any more questions yet. So far, no new questions, but if anyone has any questions, feel free to dial in and we'll try to answer them live on the air. This is Nighttime Mathematics Radio. While we're waiting, let's take a look at our favorite calculator again, the TI-30Xa. Let me go over to it. Here's once again our TI-30Xa. And this time, let's take a look at the fact that it's something people don't often notice about this thing, which is it can do fractions. There's this strange button over here that's labeled A, B over C. That's there to two fractions. So for example, if I want to write 1/2, I'd write 1, that thing, 2. That's the way this calculator represents 1/2. It's a strange looking symbol. That's because this is a very cheap display. It just uses an 8-column display, so it doesn't really have a fraction bar like you'd usually want. So it draws with that little L, that little reverse L there. How do we know this is 1/2? Well, I can multiply it by 3. And I get 1 and 1/2. That's the way this calculator represents 1 and 1/2. I can divide it by 3. Oops, I think it just added something. Let's see. Divide it by 3. 1 and 1/2. Divide it by 3 again. 1/2, divide it by 3 again. Get 1/6, as you'd expect. I can add 1/7 to that. And it goes through all the business of finding a common denominator. It gives you 13/42. Let's multiply that by 8 for a second. Just take a look. Now, this is 2 and 10/21, but sometimes you don't want a mixed number like this. Sometimes you want an improper fraction. And up above the fraction symbol, there's a d over c. That's there to get into an improper fraction. If I push second that, it gives me 52/21, which is the same number, but this time written as an improper fraction. And I can push the fraction symbol back again. I can do second that again, rather, to get back to 2 and 10/21 again. The cool thing about this is that means if you're doing simple fractions, you can actually do them right on the calculator. You don't need to work with decimals then try to work your way back again like some people do. Now, this is sort of limited. You don't want to keep doing this for bigger and bigger numbers. In fact, if you try to make the denominator too big, it will give up and go back to decimals. So if I divide this by 25, it goes 5/25. Let's divide it by 83. And now it just gave up. It said, okay, I'm not dealing with a decimal denominator that big. Here you go. Here's the decimal. Good luck. Godspeed. But the rest of the time, for simple fraction problems, this is really good. This gives you a lot of very simple ability to do the kind of things that are easy to get wrong when you're tired. You know, a half plus a third. It's something everybody can do when they're awake. If you're awake, you say, okay, fine. A half is 3/6. A third is 2/6. You add it together, you get 5/6. But if you're tired, you can get that wrong, and that's embarrassing on a bad day. So it's nice to have the calculator just there to give you a leg up when you're sleepy. This is Nighttime Mathematics Radio. I got an interesting question here from Sarah Samus asking, when is tau more useful than pi? Well, let's take a look at these. What is tau? Let's start with that. Now, this is one of these questions in mathematics that ultimately doesn't matter, but is really fun to argue about. The issue is this: where does pi come from? Remember, where pi comes from is by taking a circle and taking the two things that are really easy to measure. The things that are easy to measure at a circle are the diameter. And by measure, I mean physically measure. Obviously, if this is in a math problem, you can measure whatever you want, but in a real world circle, if you want to measure something, the easiest thing to measure is the diameter, and the reason is that you could take what are called calipers, which you've probably used in a machine shop. These are this device that looks like this, typically, like a ruler with sliding ends. And you can slide it right over the circle at its widest point and clink it together, and that'll give you the diameter. And the other thing that's easy to measure is the circumference, because you can wind a string around the circle, then lay it out flat, just unwind that thing, and that gives you your circumference. And now one thing that's always really interesting when you have similar figures, and remember, every circle is similar to every other circle. That's one kind of cool thing to think about. There's only one kind of similar circle, a circle. So one thing that comes up is people want to ask, well, what happens if I divide the two numbers I've got to get a dimensionless number? What happens if I take the circumference and divide it by the diameter? That's got to be the same number for every circle because they're all similar. These ratios between sides, or ratios between measures, are the same across all similar figures. And the answer is that comes out to be pi. And this is where pi originally came from. This is the original idea of pi. This is all well and good, except that with a lot of problems, the thing you actually care about isn't the diameter. The thing you care about is the radius, especially in math problems. And what entirely comes down to, what do you think the fundamental second measure is that you should be comparing the circumference to? Should you be comparing it to the diameter, or should you be comparing it to the radius? Does it matter? No. This is a problem which doesn't matter in the slightest. Do people argue about problems that don't matter? They argue about almost nothing else. So, if you want to, try to make your mind which one is really more fundamental, and you too can join one of the most entertainingly pointless arguments in all of mathematics. This is Nighttime Mathematics Radio. Well, everybody, it's 10:33. We've been broadcasting for about 23 minutes now. Let's see if we have any more questions on Twitter. So far, it looks like the answer is no. So let's wrap the show up for the night. This has been Nighttime Mathematics Radio. We'll be here every Saturday night from 10 p.m. through whenever people stop tweeting math questions, or 11 p.m. at the latest. See everybody next week. Good night, everybody, from Nighttime Mathematics Radio.